There are times when a single differential equation is just not enough to model a situation. Instead, you might need 2 or 3 or 100 differential equations, all working together to model a given situation. When you need multiple differential equations to model a situation, oftentimes the variables involved will cross over between equations as well. When we have situations like this, we end up using what's called a system of differential equations. So today we're going to talk about systems of linear first-order differential equations. When you see the word system come up in math class, it means that there's more than one component to it. So when we talk about a system of equations, we're talking about more than one equation. These systems might only have 2 equations in them, or they might have some larger number of equations in them. So what I have here is a system of n equations where I have dependent variables x1, x2, all the way up to xn playing a role with an independent variable of t. Now you'll notice each one of these, there's a differential equation for each of my dependent variables, where I have the derivative of x1, the derivative of x2, all the way up to the derivative of xn, described as a function of t times x1 plus a function of t times x2, all the way up to a function of t times xn. And then they all have the possibility of some function of t that doesn't involve x's at all. Now, it's important to note that a lot of these coefficient functions are likely to be 0 in any application, but the possibility of them being there is present. It gets a bit clunky and cumbersome to write these things this way. So mathematicians use this shorthand where we take all of our functions of t, so x1 of t, x2 of t, all the way up to xn of t, and we put them together into a vector and we name it capital X. You'll notice when it's written in books and in type printing places, it'll usually be a bold X there. And then we need all of those coefficient functions in our equation somehow, so we'll write all of those as a matrix. So this will be an n by n matrix with all of those a sub kk functions of t in it, all lined up nice the way they were in the system of differential equations. And then finally, we'll take all of those functions of t that don't have anything to do with x's, and we'll line them all up in a vector that's a capital F of t. Now notice all of these things could have an of t. They're all dependent on t. So t is that independent variable for us. So if we want to rewrite our system of differential equations, what it really is the derivative of capital X, and that equals that a of t matrix multiplied times my x vector. That's going to give me those equations on the right-hand side all the way up to the f of t component. And then to get the f of t component tacked on there, I add f of t. So that's another way of writing my differential equations. That whole system is represented by that single line there, as long as I know what x, a, and f are. And if you're thinking, that's great, but you know what, there's still lots of stuff going on there. There are a lot of mathematicians who would agree with you, and we can write it even shorter as just x prime equals ax plus f. Basically here we're saying, you know, the t being the independent variable, that's implied. We don't have to write any of that. So now let's talk a little bit about some vocabulary, really briefly. So we have what's called a solution vector. That x vector that I introduced, where it's my function, my x1 function of t, my x2 function of t, all the way up to my xn function of t, that's considered to be the solution vector on an interval I, as long as it satisfies the system of differential functions on that interval. Notice here in this definition it's called a column matrix because it is a single column. Vector and column matrix are interchangeable here. So now let's talk a little bit about when these solutions exist to these systems of differential equations. So we have a theorem about the existence of a unique solution. So we're going to let the entries of the matrices A of t and F of t be functions continuous on a common interval I that contains the point t sub 0. Then there exists a unique solution of the initial value problem on the interval. So as long as those functions in those matrices are continuous on the interval that we're looking at, and that interval contains our starting point t sub 0 or t naught, then we have a unique solution. Now we also have a thing called the superposition principle. You've actually already seen a superposition principle back when we were talking about higher order differential equations. Our superposition principle, when we're talking about systems of linear first order differential equations, says let x1, x2, and xk, these are all capital X's here, be a set of solution vectors of the homogeneous system on an interval I, then linear combination x equals c1 x1 plus c2 x2 all the way up to ck xk, where the ci, with I being 1 to k, are arbitrary constants, is also known as a solution of the system on the interval. So regardless of what we choose as those constants, if we take a linear combination basically of all of our solution vectors, we get another solution. And then we come back to this idea of, are solution vectors actually linearly dependent or independent? You've seen linear dependence again back when we were talking about higher order differential equations. So the definition, it hasn't changed any. So if we take our set of solution vectors of the homogeneous system on an interval I, we say the set is linearly dependent on the interval if there exist constants c1, c2 up to ck, not all 0, such that c1 x1 plus c2 x2 up to ck xk equals 0 for every t in the interval. If the set of vectors is not linearly dependent on the interval, it's said to be linearly independent. So basically, if I can combine these things in some kind of way that they cancel each other out without having it just be 0 times 1, 0 times the next, all added up, then I've got linearly dependent solutions, and otherwise they're linearly independent. To check for linear independence and dependence, you can use the Wronskian the same way that you did for higher order differential equations. So nothing has changed with that definition or being able to check for it except for the type of solutions that we're dealing with. When you're taking the Wronskian, you're basically going to build up a matrix. This time, instead of taking the different derivatives going down your columns, you're going to put all of these column matrices together into a single matrix. So you'll have the entries in solution vector x1 as your first column, the entries in solution vector x2 as your second column, and so on. And that will be the matrix that you're going to take the determinant of, taking your Wronskian to determine if the set of solution vectors is in fact linearly dependent or independent. And again, the same way it was for the higher order differential equations, if you have a set x1 to xn of linearly independent solution vectors, then what that's called is a fundamental set of solutions. And we're even guaranteed that there actually exists a fundamental set of solutions for a homogeneous system on some interval I. Again, that's not all written out and everything because we've talked about it before with the higher order differential equations. So if you refer back to that, then you've got the same stuff going on, the same rules all apply still. Again, we've done that stuff before, and now we also had a general solution for a homogeneous and a non-homogeneous higher order differential equation as well. And not much has changed in those either, other than we've replaced our lowercase x's with capital X's, and now instead of being a single variable, they represent a vector. So our general solution for our homogeneous system is going to be the linear combination of those solution vectors. And the general solution for the non-homogeneous system is going to be xc plus xp, where xc is the solution, the general solution to the associated homogeneous system, and xp is some particular solution of the non-homogeneous system.